Good morning and good day to you all. Welcome to today's webinar, Sampling and Homogenization, Challenge in the Mycotoxin Analysis. This webinar will feature content from Dr. David Steiner and is presented by EnviroLogix. The meeting chat is disabled, so please use the Q&A function on the top ribbon of your screen if you'd like to ask a question. If anyone would like to speak with staff here at EnviroLogix following the presentation, please head over to our website and submit the contact form. Now I'll turn it over to Dr. David Steiner for our feature presentation.
Yeah, thank you very much, Kevin, for this very nice introduction and also very warm welcome from my side. Ladies and gentlemen, it's a big pleasure and honor for me to present here already the third webinar on this mycotoxin series today. As Kevin already mentioned, we will focus on the challenges in the mycotoxin analysis with a special focus on sampling and homogenization. My name is David Steiner and I am currently the head of the reference material division at LVA. LVA is Austria's largest private food testing laboratory, and the main focus in our department is to produce and develop the next generation reference materials for mycotoxin testing. In general, I have more than a decade of experience in the field of mycotoxin analysis with leading positions at Roma Labs and also Valneva. As we move into the first thematic block of this webinar, I think it's important to recognize that the challenges we face in sampling and homogenization begin quite long before a sample actually ever enters the laboratory. So they basically originate in the biological and physical processes that drive how mycotoxins are actually distributed within food and feed materials. Unlike other chemical additives, which are basically distributed uniformly in a matrix, mycotoxins are produced by fungal colonies in highly localized microenvironments, which actually then results in high variability within batches and even between individual kernels when it comes, for example, to a matrix like corn. And in this slide, we can actually see the biological complexity behind different contamination patterns. And I have here listed some key bullets and some key takeaway messages. As I have already mentioned, mycotoxins rarely occur as evenly spread residues or contaminants. Instead, fungal growth is triggered by local micro conditions such as humidity pockets, temperature fluctuations, but also insect damage or suboptimal storage. To bring an example, outside the field influencing factors. These conditions actually then create so-called hotspots where only a very small fraction of kernels carry extremely high toxin concentrations, while the majority of a batch could still be completely free of a contamination. As a direct consequence, collecting a single small sample often fails to represent the true composition of the lot, resulting in false negative values or values far below the actual risk level. And another complicating factor is that certain toxin classes, including, for example, masked mycotoxins like deoxynivalenol 3-glucoside, interact strongly with matrix components. Their partial conjugation or binding can lead to underestimation when a routine testing laboratory or the analytical workflow do not fully convert or extract them. All of this means that sampling can be seen as the most critical and at the same time most error-prone phase of mycotoxin testing. And to better illustrate how extreme this heterogeneity can be, I'm sharing now some research from a recently conducted study that actually investigated contamination of mycotoxins at the level of individual kernels. This study from the University of Leida and the Cranfield University in UK provides a detailed microscale view of mycotoxin distribution, in this case in oat. The researchers investigated 2 deoxynivalenol contaminated batches and then analyzed around 200 individual kernels for in total 14 different toxins. So the overall goal was not only to quantify which mycotoxins were present, but also to understand how contamination varies from kernel to kernel, how different toxins co-occur, and how these patterns influence the batch classification. And this correlation heat map we can see here shown or shows us the relationship between deoxynivalenol and its derivatives. So the insights here help us to better understand why analyzing bulk samples can mask critical contamination patterns. And in addition, they also have a regulatory implication. So if only a small subset of the kernels drives a batch over the legal limit, then missing these kernels can easily result in non-compliance or in an inappropriate acceptance of high-risk lots. And the key findings of this study are quite eye-opening. So fewer than 10% of the kernels accounted for the entire deoxynivalenol exceedance, meaning that roughly 90% of kernels were completely toxin-free. Additionally, the authors identified a slight negative correlation between kernel weight and toxin levels, and a very strong co-occurrence between deoxynivalenol and its acetylated and glucosylated derivatives. Very crucially, when only 0.5% of the batch was effectively sampled, the probability of falsely accepting a non-compliant lot exceeded 80%. And this actually illustrates why proper sampling is indispensable. If a small test portion does not contain any of these highly contaminated kernels, the analytical result will misleadingly suggest that the batch is safe. So, having seen how dramatically mycotoxins vary within single batch or even within single kernels, the next logical step is to consider how sampling strategies must compensate for this heterogeneity. So the scientific evidence makes it clear analytical precision cannot correct for poor sampling. A robust sampling plan is therefore essential, not only for reliable measurements, but also for regulatory compliance and practical risk management across the food and feed supply chains. So representative sampling is perhaps the single most influential determinant of analytical validity in mycotoxin testing, we can conclude at this point. Because contamination is clustered, failing to capture a hotspot means failing to measure the true risk. From a food safety perspective, this can allow contaminated lots to enter the supply chain. From an economic standpoint, it can also result in unnecessary product rejection when sampling captures a rare contaminated kernel by chance. So regulations such as the European Union's maximum levels and sampling procedures are written with the assumption that the sample accurately reflects the lot. A non-representative sample therefore undermines regulatory compliance, potentially leading to misclassification, recalls, or even trade disputes. So on the next slide here, we can now see two distinct regulatory philosophies. First, the European Union's Regulation 2782 from the year 2023, which mandates large aggregate samples, often approaching around 10 kilograms, to maximize statistical representativeness across the lot or its sublots. It therefore provides a regulatory framework, but does not prescribe, for example, detailed mechanical probe geometry. Instead, it emphasizes distribution of increments and careful avoidance of contamination. On the other side, we have the USDA Grain Inspection Handbook. This is operationally focused and prescribes specific probe angles, insertion patterns, and also cleaning procedures. Sample sizes are generally smaller, but mechanical consistency is tightly controlled. So both frameworks aim to mitigate heterogeneity, yet they approach it from different angles. One through the statistical breadth and power, and the other through the mechanical precision. However, when we talk about sampling, one principle stands out across all of the regulatory frameworks and all scientific studies. Larger sample sizes dramatically improve the representativeness of a batch. The reason is rooted in simple but powerful statistics. Because, as we heard, mycotoxin contamination is clustered and not uniformly distributed. Collecting only a few increments increases the chance of missing the hotspots entirely. A small sample may look clean simply because the highly contaminated kernels were never included. By increasing the number of increments and the total mass of the aggregate sample, we essentially increase our probability of capturing those rare but also critical contaminated kernels. This is why regulatory bodies around the world, even though their approaches differ, agree on this very simple principle. The USDA explicitly emphasizes that the sample must reflect, for example, the entire truckload, often tens of thousands of kilograms. So what is critical in this context is to translating regulatory guidelines into practical action. In the United States, this includes several actions. For example, at least 7 probe insertions at a 10-degree angle are recommended for flat bottom trucks. In addition, cleaning probes between loads prevents cross-contamination, especially after high-risk grains. The European Union amends across the lot or sublot without specifying any angles in this case. Operators must handle samples very carefully to preserve integrity and also to avoid any kind of bias. Systematic documentation of sampling points and probe angles and also the quantities further support traceability and also the regulatory compliance. And following these standards ensures that downstream processes like division, grinding, and homogenization are built on a very reliable foundation. So after collecting the primary sample, it is in addition very essential to also subdivide it then properly to also create representative test portions. Randomization during this process helps to prevent a systematic error that could result from localized contamination within the collected material. Riffle or seed dividers, as we can see here, are widely used tools for this purpose, allowing repeated splitting of the sample until the desired size for grinding or analysis is achieved. Best practice recommends performing at least 2 rounds of division and homogenization. This not only improves the consistency, but also significantly reducing subsampling errors. Without these steps, even a well-collected sample can yield to misleading results because contamination hotspots might be unevenly distributed within the collected subsamples. Besides potential systematic errors that can occur during the sampling process, the sampling environments contain numerous hazards that may compromise the sample integrity. These include, for example, insect infestation, like rodents, but also fertilizer residues, mixed grains, ducted loads, foreign materials, and so on. Physical factors such as moisture pockets, dust, and uneven flow can also bias the sample. Neglecting these risks can result in over or underestimation of contamination, creating safely regulatory and also economic consequences. Therefore, pre-inspection, careful handling, and also awareness of environmental conditions help to mitigate these hazards. The key take-home messages regarding sampling is that the primary challenge in mycotoxin sampling is based on the inherent heterogeneity of large lots. So this is basically the foundation of this pyramid. Even with careful planning, toxin distribution varies dramatically within a batch, making multiple increments essential for the representativeness. In addition, limited physical access in trucks or rail cars or silos further complicates proper sampling, as certain areas may be inaccessible. Also moisture variations can affect both sampling and also the subsequent grinding, leading to inconsistent test portions. Then cross-contamination between lots is another risk, especially when equipment is not thoroughly cleaned. Additionally, operator variability results in differences in probe insertion, handling, and also adhere to procedures that also can introduce errors even in standardized operations. And finally, equipment calibration is very critical. Worn or misaligned probes and dividers can also distort sample composition. So to sum it up, addressing all these layers from inherent lot heterogeneity up to human and equipment factors is absolutely essential to maximize the sample reliability. As we move forward, representative sampling alone does not guarantee reliable analysis. So homogenization is also essential to reduce subsampling errors and also ensure consistent toxin distribution. Proper grinding and milling allow extraction efficiency to be maximized and also analytical repeatability to be achieved. By combining accurate sampling with effective homogenization, laboratories can produce representative test portions and by that minimizing the overall analytical uncertainty. So why homogenization matters? Well, proper homogenization significantly improves the extraction efficiency, as I already said, which in the end enhances the repeatability of the measurement. Very important in this case, the matrix characteristics influence the choice of the homogenization method. For example, oily seeds may smear, and that's why oily matrices like nuts or seeds, for example, require cryogenic milling. Fine powders on the other side, for example, from wheat flours or spices, increases the risk of segregation, and wet samples can generate heat during the grinding process. So by addressing these challenges, laboratories can convert a representative bulk sample into a uniform test portion and setting the stage for accurate and accurate multi and also single mycotoxin analysis. So this step also requires validated grinder settings to ensure consistent particle size, complemented by regulatory sieve checks to confirm target mesh ranges. Cleaning equipment between lots prevents cross-contamination within, which helps to maintain the sample integrity. So documentation of mill settings, but also sieve results and any deviations ensures that the traceability and also the regulatory compliance. Very crucial in this relation is the so-called mesh size, as it defines the fineness of the sample which is directly impacting on the extraction efficiency. For instance, the European regulation 2782 mandates finely ground laboratory samples, while USDA, on the other side, the guidelines specify minimum particle size checks, such as at least 60% passing a 20% mesh, a 20 mesh sieve. But what exactly is the mesh size? So per definition, the mesh size refers to the number of openings per linear inch in a screen or filter, indicating its fineness, which means a higher mesh number. For example, 100 mesh means more openings per inch and smaller holes, allowing only very fine particles to pass, while a lower mesh number, for example, 20 mesh, has larger holes for bigger particles. The numbers D10, D50, and D90 describe the particle size distribution. D10 is also known as diameter 10, indicates the size below which 10% of particles lie. D50 can be seen as the median particle size, and D90 represents the size below which 90% of particles fall. And all these metrics together allow laboratories to evaluate both the fine and also the coarse fraction of a ground sample, ensuring consistent homogenization. I have also here some examples of different examples with relation to the fineness and the mesh size. Like, for example, 60 mesh represents fine sand, and 270 mesh on the other side represents very fine lab powders. We have also a typical ground sample of 60 micrometer that can correspond to roughly a 240 mesh sieve, but the average particle size differs from the maximum particle size, which actually affects the analytical reproducibility. That means reference materials labeled as lower 200 mesh guarantee, in this case, 100% of particles pass 75% of micrometers, like here in this table, through the average particle, though the average particle may even be finer. So using this diameter matrix provides a standardized framework to compare particle size across different matrices. And building on this particle size matrix, this study from the FDA demonstrates how particle size directly affects sample homogeneity and also the mycotoxin distribution. So the authors in this case conducted first different milling techniques and performed the particle size distribution assessment for 4 different matrices, including corn, compound feed, peanut butter, and also wheat flour. So the samples were prepared using wet, dry, or cryogenic milling, and were then subdivided systematically following ISO-aligned hierarchical design. The particle sizes were then measured with a laser diffraction method, also calculating for D10, 50, and D90 metrics, providing precise insights into fine, median, and also the coarse fraction of the material. The subsamples were then tested for mycotoxins such as aflatoxin B1, deoxynivalenol, fumonisins, and zearalenol, so leading mycotoxins, via the LC-MS method. And very important in this case, for all matrices, so including the corn, the feed, peanut butter, and wheat flour, the subsamples with D90 below 850 micrometer, which can be roughly seen as 20 mesh, consistently met the AOAC's homogeneity recommendations. So the authors also included microscopic images, which are shown here for all of these different matrices, showing uniform particle distribution after grinding, which can be seen very powerful here with this image. The ISO Guide 35 ANOVA was also conducted and actually confirmed the homogeneous distribution for most mycotoxins, demonstrating that the particle size reduction is a very reliable and also a matrix independent strategy. So these results actually highlight the importance of standardized grinding protocols for achieving reproducible mycotoxin measurements. A fine particle size ensures representative analytical portions and also reduces the variability introduced during the sample preparation. So this foundation of this very well homogenized samples leads us now directly into understanding how the variability in sampling and also the sample preparation contributes now to the overall measurement uncertainty. Understanding and quantifying the measurement uncertainty allows laboratories to interpret mycotoxin results with highest confidence. So it's important to understand that analytical precision in mycotoxin testing is basically influenced by multiple layers, which are demonstrated here in these pictures. Sampling alone, for example, accounts for over 60% of the total variability due to the highly heterogeneous distribution of the toxins in bulk materials. So that's already the biggest share of the overall error. Factors in this case include the sample strategy, but also the lot size, the frequency, the probe technique, as well as also environmental conditions and also the equipment cleanness, as we have already seen in the previous slides. The sampling is followed by the sample preparation, which adds further variability through the grinding efficiency, subsampling, but also the extraction and even storage conditions. Analytical process contribute through method suitability, quantification limits, and also matrix effects, but can be seen as the smallest contribution to the overall analytical precision. Additionally, factors such as laboratory personnel, but also procedural consistency and even procurement impact the reproducibility within the lab. So in general, the measurement uncertainty quantifies the confidence in an analytical result, expressing the range in which the true value is expected to lie, typically at a 95% confidence. So what measurement uncertainties can we then typically expect with respect to different methodologies? I would like to start with HPLC UV techniques, also including FLDs. Typical measurement uncertainties are here at around 10 to 20%. The expanded measurement uncertainties in this case, which is actually very low. But in most cases, these methods simply following a single analyte analysis leading to this, I would say, rather low value. Variabilities arise mainly from matrix effects and also cleanup efficiency, for example, by using immunoaffinity columns. This is then followed by single analyte LC-MS and also high resolution MS analytical methods with measurement uncertainties at around 20 to 30%. So this can be further reduced when stable isotope labeled internal standards are used, or also matrix specific calibration are applied. Multi-mycotoxin LC-MS on the other hand already results in measurement uncertainties around 50%, and this is due to the increasing complexity and variability due to co-eluting compounds, overlapping isotopes, and differing extraction efficiencies. However, this 50% measurement uncertainty is also mentioned in other guidelines, for example, from the pesticide world, where multi-residue LC-MS analysis is having a general 50% measurement uncertainty, and this can therefore also be used as an indicator for the multi-mycotoxin methods. And finally, immunological-based methods such as ELISA, but also strip tests like LFDs often result in slightly higher measurement uncertainties, up to 80%, which is dominated by extraction inconsistencies, but also cross-reactivities and sample preparability. However, these methods are not intended for confirmatory analysis. They are often act as qualitative method for a very quick yes and no decision. So a key contributing factor applied for all these methods is the so-called lot-to-lot variation. It actually describes the systematic differences in analytical response between distinct batches of the same commodity caused by the origin, the variety, even the harvest year, or the processing differences. So this variability is generally triggered by different matrix compositions, including variabilities in their lipid, but starch, sugar or pigment profiles, which then increases the co-extraction of matrix components and in turn influences on the extraction efficiency on the one hand, and also on the ionization performance in the LC-MS setting on the other hand, generating so-called relative matrix effects. These differences directly impact on the so-called apparent recovery, which can be seen as a combined recovery effect, taking the matrix effect, but also the losses through the extraction into account, and with that also on the measurement uncertainty. When a method validation, for example, is performed only in a single lot, these between lot effects are simply ignored or neglected, leading to an underestimation of the overall uncertainty. By recognizing the lot-to-lot variation as a major contributor in this analytical setting, we better understand why complex multi-mycotoxin, especially LC-MS workflows, often require a very pragmatic, expanded uncertainty of around 50%, encompassing both analytical variability and also the sampling heterogeneity. And to quantify the impact of the lot-to-lot variation, a study was conducted by my former colleagues at the Boku University, where they actually assessed the expanded relative measurement uncertainty for a multi-mycotoxin LC-MS method covering around 66 analytes. So the assumption was that routine recovery measurements typically rely on replicates from a single spiked lot, neglecting the matrix differences between different lots completely. So the study therefore compared two approaches. First one using 7 replicates from one lot, and the second approach using 1 replicate from each of 7 distinct lots. So 7 different lots of one matrix commodity, including 2 different matrices. One was for figs, as we can see here on the left side, and one for maize or corn. You can see here on the right side. And the results were quite clear. So differences in matrix composition between lots affected the extraction efficiency and also the matrix effects, which were not captured in the single lot replication. And therefore, this approach provided top-down estimate of a more realistic uncertainty for multi-analyte methods. Including the lot-to-lot variation significantly increased the expanded measurement uncertainty. So the median uncertainty for evaluated analytes rose from approximately 21 to 24% when using single lot to about 31% when multiple lots were considered, representing around 30 to 50% of relative increase depending on the matrix. We can see here the comparison for figs and maize in this graphic. The matrix-specific drivers differ actually. So for figs, for example, the increased uncertainty was mainly due to differences in analyte recovery, whereas for maize, the relative effects were the relative matrix effects were actually the dominant factor. And given the complexity of multi-LC-MS methods and impracticality of performing full bottom-up uncertainty budgets for every analyte, a pragmatic default of around 50% expanded uncertainty provides a very conservative fit-for-purpose approach for this kind of broad analytical mycotoxin settings. So the value captured in the Santé guide for pesticide analysis can therefore also be applied for the multi-mycotoxin, or I would even say for multi-class methods in general. So having now explored the sources of variability and the impact of the lot-to-lot differences on the measurement uncertainty, we now shift towards the practical strategies to improve the routine mycotoxin testing. So reliable sampling, homogenization are essential, but the laboratory practice, the quality control, and also the reference materials play a very crucial role in ensuring accurate, but also especially defensible results. So in this case, we talk here about confirmatory routine laboratory work. When it comes to reference materials, we have to distinguish between, I would say, typical reference materials, which are substances with a very well characterized property or properties used to calibrate instruments, but also evaluate methods or assign reference values. On the other side, we also have so-called certified reference materials. They extend this by providing traceable, certified property values accompanied by documented uncertainty, offering regulatory compliant benchmarks. QCMs or quality control materials are one very important part of this reference material world, as they play a key role in this setting, and they can be used in different stages in different stages of the analytical setup. For example, in assessing the accuracy, verifying method linearity, also conducting recovery studies, and also monitoring precision over time within, for example, a laboratory control chart. So they allow a laboratory to evaluate the method's robustness, also identify bias, and also quantify the measurement uncertainty reliably. In other words, without proper reference material, a routine testing laboratory cannot really guarantee the highest analytical standard. And in my last slides, I have therefore prepared two materials I want to share with you, which were developed very recently. The first material is a maze-based quality control material, which actually demonstrates how naturally contaminated samples can be transformed into a uniform practical reference material. Here at the LVA, we have developed such a material by mixing together highly contaminated maize lots with regulated but also emerging mycotoxins. And this process actually started with blending a small mycotoxin contaminated portion with clean maize, a blank maize, followed by ultracentrifugal milling using a 0.25 millimeter ring sieve to standardize the particle size. We did, in this case, this in several rounds and always measured the homogeneity of the lots in between by LC-MS, and the resulting material at the end achieved a D90 particle size of between 200 and 250 micrometer, which can be seen of around 70 mesh. So you can really say it's a really fine powder. And the final material was then characterized through an interlaboratory study involving in total 13 different international laboratories. For example, national reference laboratories from Italy, Poland, Serbia, Croatia, also accredited universities, and also big business laboratories. These labs delivered us 15 data sets, including reference methods like LC-MS, but also high-resolution MS, but also quick tests like ELISA methods, for example. And this study actually confirmed the reproducibility and allowed the establishment of reference values for all regulated mycotoxins and also indicative values or informational values for emerging mycotoxins like 3 and 15 acetyldeoxynivalenol, but also fumonisin B3. The characterization of the material involved rigorous statistical evaluation to ensure also reliable reference values. So outlier detection was conducted first via a so-called groups test, while a distribution assessment guide the choice of mean and standard deviation for a normal distribution and median absolute deviation for a non-normal distributed data set, delivering us a very robust statistical outcome. In the MACE quality control material, basically both ISO 17025 accredited laboratories, here listed from lab 1 to 8 on the upper part for aflatoxin B1, and the non-accredited labs, here the lower part, lab 9 to lab 15, actually provided a very realistic assessment of the analytical performance across diverse environments, actually underlining that the choice of these laboratories was very well done. Also, the non-accredited labs did a great job in this case. Statistical comparison also revealed that there were no significant differences between the different lab settings, demonstrating the robustness of the quality control material across different laboratories. This can be here seen with the two different box plots, and such analysis actually ensures that certified or indicative values are valid, reproducible, and also suitable for method verification. What makes this material now so special is, first, it's built on fully naturally contaminated raw materials, which perfectly reflects real-life conditions and posing practical challenges also for laboratories like heterogeneous toxin distribution and also matrix effects. The homogeneity is verified in accordance to ISO 17025 standards, and a stability study will be performed or is still ongoing for several years. And by incorporating these values into laboratory workflows, analysts can really validate their methods and monitor their performance and confidently interpret their results at the end. This approach at the end bridges the gap between theoretical measurement uncertainty and also practical analytical reliability, creating a framework for accurate, reproducible and reproducible mycotoxin testing by using only one single material. And the second material I want to talk about now is a material which was produced by the working group in Canada, by the Canadian Grain Commission. So we have now more or less talked about proficiency test or settings where only the sample preparation or the analytical precision was in the focus. Now we want to shift the focus a little bit more into the area of the sample preparation step, and therefore a recently conducted study from colleagues in Canada investigated exactly this by using deoxynivalenol fortified wheat kernels. So instead of focusing solely on the analytical performance, the authors here produced a dough-based test material created from an aqueous deoxynivalenol solution and durum wheat in this case, which was subsequently shaped into spiked tufta kernels. And these kernels were then incorporated in 12 pieces per kilogram into clean durum wheat to produce realistic whole grain test samples. So the design in this case enabled the controlled comparison of in-house sample preparation performance, contrasting in this case a good, where the entire sample was grinded, and a rather bad homogenization approach where just a subsample of the entire sample was grinded. By integrating this sample preparation into quality control evaluation, the study actually highlights a crucial step which is often overlooked in conventional proficiency testing schemes. And this deoxynivalenol variance study produced 3 major outcomes that have direct relevance for routine grain testing. First, the researchers successfully generated a realistic whole grain test sample, allowing a structured evaluation of how different laboratories prepare and homogenize naturally reliable matrices. Second, the controlled incorporation of spiked pasta kernels made it possible to quantify the impact of sample preparation performance, isolating variants linked specifically to grinding and combination strategies. And this is hereby shown in this picture, where the results of this kind of proficiency test scheme are summarized. And this research clearly showed a very large variance between the laboratories when especially suboptimal homogenization was used, for example, when only a fraction of the entire sample was homogenized. And in contrast, grinding the entire test sample significantly reduced variance across replicate measurements, emphasizing the importance of processing the full laboratory test portion. Finally, the study demonstrated that the analytical method itself contributes to the variance, reinforcing that sample preparation, matrix homogeneity, and also the instrumental analysis cannot be evaluated independently, but function as an interconnected system. And bringing all these findings together now, several core messages emerge that can or that connect the previous discussion on sampling, homogenization, reference materials, and all these controlled test samples. I think we all agree on the fact that mycotoxins are inherently heterogeneous, making representative sampling the foundation of reliable and also compliant measurements. Particle size reduction remains one of the most effective strategies to achieve analytical homogeneity, while most measurement uncertainty continues to originate from the sampling and also the sample preparation stages rather than the instrumental variability itself. Reference materials and control test samples, as just shown, such as this deoxynivalenol fortified kernels or the next generation reference material, offer very powerful solutions to evaluate and also to improve the method performance under very realistic conditions. The overall or overarching principle is very straightforward. Keep the grain size small, keep the sample size large, and your mycotoxin results are then accurate. And with that, I'm already at the end of this webinar. Thank you very much for your attention, and I'm looking forward to your question.
Thank you for another great presentation, David. That was a lot of detailed information to absorb and help improve our sampling practices. For our audience around the world, please be aware we will be sharing this video online so you can spread the information around your organization. And we have some questions to review while we still have some time with David. So our first question, why is a 20 mesh particle size often recommended even though finer grinding would give better homogenization?
That's actually a very good question. And I was also thinking about that when I prepared the slides, because we saw that our material, for example, is a very fine powder. And actually, we have received very good feedback also from our lab so far. Although finer particle size increases homogeneity, the particle size must also fit the extraction conditions, I would say, of the final test method. So especially many quick and rapid tests, or let's say field-based methods, do not really operate under controlled laboratory conditions and use relatively mild extraction solvents, in many cases water-based solvents, and very fine powders in this case can trigger clumping, or just simply show poor solvent penetration, which then in the end reduces the extraction efficiency and causes also an underestimation of the mycotoxin levels. A 20 mesh size in this case is therefore, I would say, the best compromise between an acceptable homogeneity and also reliable extraction. In simple low energy workflows and in contrast, LC-MS under laboratory conditions can work with much finer materials because the extraction, I would say, is more tailored and controlled.
Okay, good to know. Our next question. Why do mycotoxins often form hotspots? And why is it difficult to fully extract them from different matrices like maize, wheat, or nuts?
Yeah, I think I have talked about that a little bit at the beginning, but of course I can highlight it a little bit deeper now. So different physical structures of matrices strongly influence mycotoxin distribution and also the extractability. In grains such as maize or wheat, what you mentioned, the fungal growth and mycotoxin accumulation can penetrate deeply into the cell wall, into the germ, or even into the endosperm. So this internal localization can make the extraction very difficult, especially for very polar or bound mycotoxins. In nuts, on the other side, or I would in general say oily seeds or oily or rich matrices with a very high lipid content, shells or dense seed coats can physically hinder some solvent penetration and also reduce the recovery in this case. So, and I think I have also mentioned the term masked mycotoxins already. They can bind to sugars, proteins, or other matrix components, and this further complicates the extraction. So consequently, extraction protocols must be adapted to the specific matrix, considering different factors such as the particle size, as I showed to you, and also the solvent composition. We have talked about that in our last webinar, and also the mechanical disruption to ensure at the end the representative and efficient recovery of both the free and also the bound mycotoxins.
Definitely a challenge.
Definitely.
So why do you think many proficiency tests still focus primarily on analytical performance and not on the sampling stage?
Well, probably from an historical point of view, but I would say classical proficiency tests focus on analytical performance because it's reproducible and it can be compared across many different laboratories under standardized conditions. Sampling, on the other side, is highly situational. So you have lot size, you have the truck geometry, you have the environmental conditions, and available equipment also differ widely and cannot be harmonized in an interlaboratory scheme, I would say. This makes a fair comparison between participants extremely difficult. So only recent studies, what I showed is the Canadian Grain Commission work, have demonstrated practical ways to evaluate at least the sample preparation step and the homogenization under controlled, but more controlled and realistic conditions. In routine practice, laboratories rarely control the primary sampling. They receive a pre-collected sample, meaning that most sampling responsibility lies with the customer. So unless the laboratory explicitly offers on-site sampling services. So when sampling is performed by trained personnel, established guidelines such as this European Union regulation or also the USDA handbook I showed to you should be followed. I think everything is captured in there, and these developments just basically show that proficiency testing should be gradually expand also to maybe include at least sample preparation in the future, and not only solely focus on the instrumental side.
Yeah, I think that really stresses how important that first link in the chain is.
Definitely.
And you touched on the topic a little bit, but if homogenization is capable of reducing the within laboratory analytical variation to very low levels, why do labs still exhibit significant differences in the interlaboratory comparisons?
Well, homogenization reduces the variance only when the entire sample mass is processed properly. Many labs grind insufficient mass, divide before adequate milling, or use mills that actually generate incomplete particle size reduction. So the differences in the equipment conditions, the cleaning, but also the operator behavior further increase here the variability. Additionally, some matrices are inherently difficult to homogenize, especially these lipid matrices with a very high lipid content, like nuts or oily seeds. Or also, they are very sticky, but also high sugar materials are quite complicated. So even when the particle size matrix looks acceptable, on the other side, subsampling practices may still introduce then the error. So interlaboratory studies in this case revealed that this is a practical problem, showing that the theoretical advantage of homogenization are not always achieved in routine workflows.
Okay, thank you. I think we have time to squeeze in one more. This question is about decision making when we're near maximum levels. You spoke about an expanded measurement uncertainties of around 50%.
Yes, so I mean, labs rely on decision rules that account for the uncertainty, such as, let's say, safe side interpretation, or let's say guard bands. For example, a result slightly below the maximum level is not automatically accepted. It is if the uncertainty range overlaps with the limit. Likewise, a result above the limit must exceed it convincingly before a lot is rejected. So many regulations therefore allow the use of expanded uncertainty in conformity assessment to avoid an unfair classification. Therefore, even with a high uncertainty, decisions remain defensible when interpreted statistically and documented properly. So the goal is not absolute precision, but correct risk classification under realistic field conditions, I would say.